Automatic modulation classification for low-power IoT applications. Nowadays, there is a fixed spectrum assignment policy of wireless networks, leading to inefficient utilization of the spectrum. Because most of the available frequency bands are already statically allocated to dedicated wireless systems and services for exclusive use, the radio spectrum seems crowded. However, most of the spectrum is largely underutilized in lots of areas and times. This situation is generating spectrum shortage issues while more and more devices demand wireless connectivity. Cognitive radio could represent a solution to this problem. This is because cognitive radio allows opportunistic usage of the spectrum, giving the opportunity to a secondary user to exploit the spectrum allocated to a primary user. With the use of cognition, all the unused spaces in the spectrum at a certain moment could be sensed and used by new users. The main condition for cognitive radio networks to properly function is that secondary users do not have to cause an interference to primary users. For this reason, they must sense the spectrum to decide whether or not a primary user is using it. The cognitive radio technology can be incorporated into IoT networks to maximize the spectrum utilization and improve the system performance. Nowadays, there are many different spectrum sensing techniques, but on this project, we focus on modulation classification. According to this technique, the detection of a modulation scheme employed by a primary user would be enough to ensure the existence of the primary user's signal in the frequency channel. To perform the modulation classification, we choose to design an artificial neural network with feature extraction. This modulation identification technique enables a more efficient usage of the spectrum and helps reducing the power consumption because it does not require the use of training or pilot sequences. Apart from that, this method does not require any prior knowledge of the signal parameters or channel. We also choose a feature-based classification method because they are known for offering good performances with low computational complexity. Our design classification model consists of two parts: a feature extraction stage that receives the signals and obtains the different desired features from them, and the actual artificial neural network that uses the calculated features to decide which of the 7 possible modulation schemes corresponds to each of the signals. It is important to notice that we make use of the RadioML 2016.10a standard open dataset for training, validating, and testing our model. During the feature extraction stage, we obtained 9 features from each signal. These features were selected from a bigger set of possible features using the maximum relevance minimum redundancy criterion of the mutual information algorithm. The designed artificial neural network has only one hidden layer of 15 neurons, making it suitable for applications on low-power devices with limited computational resources because of its low complexity and small number of parameters.